Good day, everyone. So our topic is about hydrocarbon. I am Dr. Erwin R. Abrencillo. For our learning outcomes, we have the following. Describe the properties of hydrocarbon. Determine the steps in writing a correct chemical name and formula for hydrocarbon compounds. Name and create chemical structures of hydrocarbon. So for our lesson outline, we have the following. First is we are going to tackle about the introduction to hydrocarbon, alkanes, alkenes and alkynes, and properties and chemical reactions. So let us begin with the first in the lesson outline, which is the introduction to hydrocarbon. So the simplest compound or the simplest organic compounds are hydrocarbon, which contains only the elements carbon and hydrogen. So how many compounds can you make by combining carbon and hydrogen? So if your guess is there will only be one, then you are wrong because there are a lot of compounds that can be composed by combining carbon and hydrogen. So thousands of hydrocarbons are known, each containing only the elements carbon and hydrogen. So just imagine um, there are thousands of hydrocarbon compounds, but they are only made of two elements, and these are carbon and hydrogen. So the simplest one of them is CH4, which is known as methane, consisting only of one carbon atom bonded to four hydrogen atoms. So in the previous video, you have learned that carbon has four valence electrons. So therefore, it has the ability to bond with four electrons. So in this case of hydrocarbon, carbon can bond with four hydrogen atoms. So this substance called methane is an excellent fuel and is the main component of natural gas. So as you can see on the right side of the slide, you have there the LPG, no? So the LPG is the source of flame in our daily uh, cooking of our food. So these are, before we proceed to the different hydrocarbons such as alkane, alkenes, and alkynes, let us look into the types of organic compounds formula because as we go along with the alkanes, alkenes, and alkynes, as well as with other functional groups, you are going to encounter these different organic compounds formula. So we have molecular formula, empirical formula, condensed formula, displayed formula, structural formula, and skeletal formula. Though sometimes there are some changes in the name of the formula, but um, it has the same meaning. So for example, you have here molecular formula. So simply shows the number of each type of atom present. It tells you nothing about the bonding within the compound. So you cannot see any bonding. You cannot see whether it is single, whether the formula has single, double, or triple bonds. So, for example, we have here C4H8O2. So you cannot see there how many bonds or what type of bond, no? So whether it is single, double, or triple bond. Now, the next one is empirical formula. So the empirical formula of an organic compound gives simplest possible whole number ratio of the different types of atoms within the compound. So that means that it is almost the same as that of molecular formula. It's just that it is in a lowest term. So for example, we have here C2H4O. So you just simply divided the molecular formula by 2. So C4 divided by 2 is 2, 8 divided by 2 is 4, and then 2 divided by 2 is 1. So in this case, you have here C2H4O1 or C2H4O. Now, Most of the time, you will encounter condensed formula, displayed formula, structural formula, or skeletal formula. So what is a condensed formula? So condensed formula is also text-based. Here, each carbon atom is listed separately with atoms attached to it following. An exemption is cyclic pairs of molecules. Example is benzene, where the carbons are grouped. So you have here CH3, CH2, CH2, COOH. So, well, you cannot see the bond, whether it is single or double bond. However, you can see here the number of carbon as well as the number of hydrogen bonded to the carbon. Now, we have another which is displayed formula. So a displayed formula shows all of the atoms in all of the bonds present in an organic compounds. The bonds are represented as lines. So meanwhile, compared with that of the condensed formula, you can see here that you can be able to identify the type of bond or whether it is single or double or triple bond between the atom. Now, for example, you have here C bonded with H, so there's a line here, signifies a single bond. Meanwhile, on the rightmost part of the formula, you have here C double bond with O, then C double bond with a single bond with O, and C again single bond with another C. You can see here in the displayed formula that um, carbon has a maximum bonds of 4. So that means it follows the rules, no, that carbon has 4 valence electrons, therefore it can covalently bond with 4 electrons also. So in this case, double bond O, single bond O, and single bond C. So you have 1, 2, 3, 4. Okay, so in a displayed formula, you can see all of the atoms as well as all the bonds present in the formula. Another one is structural formula. It is almost the same as that of the displayed formula, but not all bonds are shown. So although all atoms are still indicated using subscript numbers, carbon-hydrogen bonds are often simplified. So I think this one is, if you would like to make a formula in a shorter period of time, and you may use this one, no? You can see here the kind, whether it is single or double bond, but this one highlighted the functional group, which is COOH, and the double bond to the O. Meanwhile, for the bonding between carbon and hydrogen, so um, there's no single bond, but it is understood since carbon has 4 valence electrons, no? So in this case, you have here CH3. So it means that for each carbon, there are 3 hydrogen, and carbon is also bonded with another carbon, making it 4 bonds. Another one, I think, that is the easiest to write is the skeletal formula. So in a skeletal formula, most hydrogen atoms are omitted, but it is understood that it is there. And line ends of or vertices represent carbons. So for each um, end line, no, just like this one, just follow the arrow. This one, this one, this one, and this one. So these are carbon 1, 2, 3, and 4. So just like the displayed formula, so we can count here 1, 2, 3, 4. So you can use this as pattern, this displayed formula, the structural formula, actually all of this can serve as pattern, but as specifically a displayed formula and structural formula, you can be able to see here the number of carbons. So for each vertice or vertices or line ends or end of the line. So there is carbon here, except when there is a structure or when there is a group of atoms at the end of the line. So for example, here is an OH. So that means that this end of the line is not a carbon, but it is attached to oxygen. So again, we can count the number of carbon for each line end or end of the line. So 1, 2, 3, 4. So this skeletal formula is the same as that of the structural formula, displayed formula, condensed formula, empirical formula, and molecular formula. Okay? So again, most of the time, we are going to use condensed, displayed, structural, and skeletal formula. So let us continue. So let us look into the multiple carbon to carbon bond. So a while ago, I've said that it is possible to have single, double, or triple bonds. So carbon atoms can bond to each other, not only by single covalent bond, but also by double and triple covalent bonds. So because of that, we have these types of or class of hydrocarbon. We have here alkanes, composed of a single bond, alkenes that has they have double bond, and alkynes they have triple bond. And then we also have aromatics, or what we call as arenes. Now, the name of this hydrocarbon depends on the number of bonds that they have. So, alkane, alkenes, and alkynes. So, alkane ends with ane, and alkenes end with ene, alkynes end with yne. Now, a hydrocarbon having only single bond is defined as a saturated hydrocarbon. So alkane is a saturated hydrocarbon. Meanwhile, alkenes, alkynes are considered as unsaturated hydrocarbon because they have at least one double or triple bond on their structural formula. So these are let us talk about alkanes now. So alkanes are hydrocarbon having only single bonds between atoms. So these are straight chain hydrocarbon. Okay, so for example, you have here molecular formula, and then you have here condensed structural formula. So these are the names, and you have to be familiar with this because until the last functional group that I'll be featuring in this video, we will be using these names. Though the ending will be changed according to the functional group, but it is almost the same thing. All you have to do is to memorize the root word like methane, met, ethane, ETH, propane, PROP, butane, BUT, pentane, hexane, heptane, octane, nonene, and decane, represented by the number of carbon. Methane is 1, ethane is 2, propane is 3, 4, 5, 6, 7, 8, 9, and 10. Now, it is a straight chain because there are no branching out from the parent chain. Straight chain because simply it is straight. Like this one, stage 4, all of these samples. Now, another one is, alkanes are hydrocarbons that have only single bonds between atoms. Yes. And these are, again, samples of straight chain alkanes. You have here, the one on the right are common examples like ethane. And then on the left side is the one that I have shown you a while ago, the different samples with the molecular formula and condensed structural formula. So again, in the condensed, you cannot see here whether it is single, double, or triple bond, but it can be shown by counting the number of attached um, atoms to the carbon. On the right side are common examples. You can see here also the ball and stick model. So the ball and stick model allow us to see the 3D structure of our compound. So you can see here that they form a certain shape, no, following the BSEPR theory of the model. Now, let us proceed now to some explanation as to what straight chain alkanes are. So it is a series of compounds that differ from one another by a repeating unit is called a homologous series. So the one that I have shown you a while ago, like CH4, CH3, CH2, CH3, 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 CH2, CH2, CH3, and so on and so forth. All right. Now, a homologous series has a fixed numerical relationship among the number of atoms. So that's why you can use a formula like CN H2N plus 2. Okay, so where N is equal to the number of carbon atoms in the alkane. So given the number of carbon atoms in an alkane, you can write the molecular formula for any alkane. So for example, a heptane has 7 carbon atoms, so its formula is C7H2 times 7 plus 2 is equal to C7H16. All right. So let us now look into the branch chain alkane. So it is easier for us to determine if it is straight chain alkane. I just have to simply count the number of carbon and then just select whether it is methane, propane, butane, pentane, hexane, heptane, octane, nonene, and decane. Now, if you think, now, I want you to look into this and tell me whether they are the same. Well, if your answer is they are different, then you are correct. Now, however, you might also see here that they have the same molecular formula, which is C4H10. The first one on top is a butane, which is C4H10, and the one at the bottom is isobutane with the same molecular formula of C4H10. Well, if you are having doubt, you can still count, no? So the one at the center are carbon, and the one at the blue ones are the hydrogen. Now, so the structure on top represents butane. The structure at the bottom represents a branch chain alkane known as isobutane. So they have a very different chemical and physical properties from each other because of the branching out of alkane. So carbon atoms can bond to 1, 2, 3, or even 4 carbon atoms. This property makes possible a variety of branch chain alkanes. So these are some of the common alkyl groups that can branch out from the parent chain. So because of the branching out, there is the formation of what we call as alkyl group. So alkyl groups can, the name of the alkyl groups can be taken out from the name of the alkane itself. So however, it will end with YL instead of ANE. So that's why methane will become methyl, ethane will become ethyl, propane will become propyl, and so on and so forth. Um, you can see here the condensed structural formula of each of the alkyl group, and then also the structural formula. Now, let us name some of this example. No, so these are the steps in naming branch chain alkanes. So you have to remember that when we give name to any organic compounds, we follow the IUPAC system of nomenclature. So IUPAC is the International Union of Pure and Applied Chemistry, the one who set the name for uh, organic compounds, as well as in charge of other concerns about inorganic and organic chem, or any chem for that matter. So these are the steps. So you have here 6 steps. These are actually easy steps. So let us just identify these steps, and it will be easier for us to use this in an example that I will show you on the next slide. So step 1, count the number of carbon atoms in the longest continuous chain. So you have to remember, when you count the number of chain, it should be continuous chain. You have to look into the longest chain possible, since they are branching out. So the next one is to number each carbon in the parent chain. You have to count the number of carbons. So if there are 6, it will be hexane. If there are 7, it will be heptane. If there are 8, it will become octane, and so on and so forth. Then after that, you have to name each alkyl group substituent. So the one that you did not include in the number of carbon, when you count it, will become the alkyl group. Then you have to name them. Is it a methyl? Is it an ethyl, a propyl, a butyl, and so on and so forth. And then in the step 4, if the same alkyl group occurs more than once as a branch on the parent structure, use a prefix di, tri, tetra, and so on before its name to indicate how many times it appears. Then use the number of carbon to which each is attached to indicate its position. So you have to identify the position of this alkyl group, and then you have to use the prefix they if there are more than one in the chain. For example, you have found there that there are 2 methyl, so you call it as dimethyl. If there is only one, so you will not write any like monoethyl. No, you have to start with 2 alkyl group that are the same. So you have to start with di, but never in mono. Then when different alkyl groups are attached to the same parent structure, place their names in alphabetical order. So let's say, for example, you have their ethyl and then methyl. So you have to write first ethyl and then methyl, not methyl and ethyl. And then you have to, of course, you will disregard whether you are using prefixes. Meaning to say that, for example, it is diethyl. So it is not the D for di, but it is the E for ethyl that you are going to consider for the alphabetical order. Then after that, write the entire name using hyphens. Step 5, different alkyl groups. Yeah, I'm done. I am done with that. So step 6, write the entire name using hyphens to separate numbers from words and commas to separate numbers. So you have to remember all these steps. And this is a standard, and meaning to say, when you violate one, your name will not be marked as correct. So make sure that you will follow each step, because we are talking about the name of the compound. So if our name in our birth certificate is very sensitive and it follows certain rules, so same thing as with the name of compounds. So you have to write their names carefully. So these are, let me show you an example. So sample problem we have here on the right, name the alkene shown. This is our sample. So this is branch chain alkane. So let us name this one, and let us follow the 6 steps that that I have shown you a while ago. But we can summarize this into 3 steps. So step 1, step 2, and step 3. So the first one is to analyze the problem. First, you have to begin with an analysis. So what now? So you are given a structure, you are given a problem, and then you have to determine the name of the parent chain and the names of the location of branches. Follow the IUPAC rules. So those are the 6 steps that I have shown you a while ago. So solve for the unknown. So count the number of carbon atoms in the longest continuous chain. So I have presented here two possible counting. Okay. So the first one is the usual count. When we count, we start with the left going to the right. So 1, 2, 3, 4, 5, 6, 7, 8. On the other hand, I have also counted that from right to left, 1, 2, 3, 4, 5, 6, 7, 8. Well, of course, you cannot just go up because there are only 5. 1, 2, 3, 4, 5, 6. There are only 6. Cannot just go down like 1, 2, 3, 4 or 1, 2, 3, 4, 5, 6. So the longest possible is 8 carbon. So that is octane. So the parent name is octane. But you are not yet done because you are just starting to name the compound. So step 2 is to number each carbon in the parent chain. So since you are still confused whether you are going to use this on the left or on the right, so you have to assign number. So in this case, we assign from left to right as 1 to 8. On this side, we assign from right to left as 1 to 8. So which of the two are you going to use? Now, um, according to the rule, you have to select the lowest position number. Okay, lowest position. So on the left side, the position of the substituents or the alkyl group is 4. We have here methyl, methyl, and ethyl. So you have here 4, 5, and 6. Meanwhile, on this side, we have 3, 4, and 5. So which one is lower? So of course, basically it is the 3, 4, and 5, the one on the right. So we are going to use this, this one on the right. So the next step is to name each alkyl group, identify and name the alkyl group branching from the parent chain, and assign number. No, so you have here we have here methyl. You have 2 methyl found on the 3rd and 5th carbon, and you have 1 ethyl found on the 4th carbon. So there's only one ethyl group, so you will not be using any prefix. But for the methyl, there are 2 methyl, so you'll be using prefix like di, so dimethyl. And of course, you have to include the carbon location. For ethyl, it is found on the 4th carbon, so you call it as 4-ethyl. And then for the methyl, there are 2 locations, that is the 3 and 5. So you have to write 3, comma, 5 dash dimethyl. Okay, so you are good to go for step number 5. So whenever different alkyl groups are attached to the same parent structure, place their names in alphabetical order. So therefore, we write ethyl first before dimethyl. So E first before M. Okay, so write the entire name using hyphens to separate numbers from words and commas to separate numbers. And then write the name of the structure using hyphens and commas as needed. The name should be written as 4-ethyl, 3,5-dimethyl octane. So let us evaluate the result. So you have used here the longest continuous chain, 1 to 8. All branches have been designated, ethyl and then 2-methyl. Alphabetical order and punctuation are correct. So 4 dash ethyl dash 3, comma 5 dash dimethyl octane. So that's how you do it. Now, basically, this will also be the same steps, almost the same steps for alkene and alkynes, as well as in other functional group. So that's why you have to master this one first before you can proceed to the next part of the video, so that it will be easier for you to name and to draw chemical structures of alkenes and alkynes. So let us now proceed also with cycloalkane. So one of the reasons that such a variety of organic compounds exist is that carbon atoms can form ring structures. An organic compounds that contain a hydrocarbon ring is called a cyclic hydrocarbon. So this is cyclic. Cyclic because it is like a cycle. So to indicate that hydrocarbon has a ring structure, the prefix cyclo is used with the hydrocarbon name. So like cyclopropane, cyclobutane, cyclopentane, and so on. So the cyclic hydrocarbons that contain only single bonds are called cycloalkanes. So you also have cycloalkanes and cycloalkynes. So the one on the right is the different formula. You have here skeletal structure, then condensed structural formula, and then line structure. So you have here the sample problem. So name the cycloalkane shown. So we will follow the same format of naming. So you have to remember the longest continuous chain. So we are talking about cycloalkane. So it is obvious that it must follow the shape. Another is that when there are attached alkyl group or any substituents, it must follow the ruling about the lowest combination number. So first step, analyze the problem. You are given a structure, determine the parent cyclic structure in the location of the branches, follow the IUPAC rules. So I have presented here two possible scenarios. So one is counting by counterclockwise, and then the other one is counting it by clockwise. Now, you have here two combinations. So we have here 1, 3, 4 for the location of the methyl group. So you have here 1, 3, and 4. On the other side, you have 1, 2, and 4. So you have to select the lowest number, 1, 2, and 4. You might ask, can we start in anywhere in the cyclic? Yes and no. Yes, you may do so, but make sure that it is beginning with an alkyl group, wherein when you circle around the structure, you will have the lowest combination number for the position or location of the alkyl group. So the third step, name the substituents. So there are three methyl groups. So you have on the step 4, you have to use the prefix tri, and then you have to alphabetize, but there's only one group present, so there's no need for you to alphabetical it or alphabetize it. And then step 6, put the name together using the name of different cycloalkane. Use commas between separate numbers and hyphens between numbers and words. Write the name as, so you have here 1, 2, 4, trimethyl cyclohexane. So there's only one name here. So again, you have to evaluate it. So let us talk about alkenes. So these are considered to be as unsaturated hydrocarbon that contains one or more double covalent bonds between carbon atoms in a chain are called alkenes. So because an alkene must have a double bond between carbon atoms, there is no one carbon alkene. So the simplest alkene has two carbon atoms double bonded to each other. And then the remaining four electrons from each carbon atom are shared with four hydrogen atoms to give the molecule ethene. So there's no methane from methane because there should be double bond for it to be considered as alkene. So these are common or examples of alkenes. You have here the molecular formula, structural formula, and then condensed formula. Now, from between these two, except for the molecular formula, you can see here the double bond. So the double bond will tell us that it is an alkene. However, in the molecular formula, you can still identify that it is an alkene, but it is a bit complicated. However, as long as you can see here that there's double bond, then it is understood that it is an alkene. So this is how you name it. So when naming either branch or straight chain alkenes, they must be numbered using IUPAC rules. So on this one, you have here 1-butene. So it is 1, 2, 3, 4. So the carbons located on the 1-butene. On the first carbon, you have also here 2-butene. And then you have here 1-butene. Why it is 1-butene? Because in naming alkene, the priority is the location of the double bond. So you have to look into the location of the double bond and check whether it is located on the left or right side of the formula. Now, there's no 3-butene because instead of 3-butene, so you have to count it as 1-butene instead because it is now located on the right side of the chain. Then you have here also straight chain alkenes. So this one. Then on the second one is the cyclic alkene, which is like the cycloalkanes. You can see here the double, uh, the double band in the structure, and then you make sure that when you count, you have to pass the double band. It's the same thing when you count here from the first to second carbon, no? So you have to pass the double band. On the second on this cyclic alkene, you have to pass the double band. You cannot just go around, no? So your priority now is the double band. On this example also, you can see here that um, it is also taken for consideration the alkyl group, which is on the third carbon, because you're going to start here in the 2, then going to count 1, 2, 3, 4, 5. The methyl group will be located on the fifth carbon, which will also violate the IUPAC system or the IUPAC ruling. Now, you may look into this one, no, 1, 2, 3. So it is now located on the third carbon. So that's why you may, this is the correct numbering of the carbon in these cyclic alkenes. Now, the position of the double bond in the alkenes are numbered in a way that gives the lowest set of numbers. This is true of both on both branch and straight chain alkenes. Let us look into this. This one is a single double bond, and this one is two double bonds. So you have here two methyl butene. You have here 1, 2, 3, 4. So it is located on the first carbon. It is easier to identify. It is closer to the left. So you have to start with the left. Though there's a chain here, an alkyl group, which is methyl. Now on letter B is the two double bonds. Wherein there are two locations. So if you count it from left to right, it is located as 3 and 5. So 1, 2, 3, third carbon, or 5, fifth carbon. However, if you choose to start on the right side going to the left, you can see here 1, 2, it is found on the second carbon, 3, 4 on the fourth carbon, 5, 6, 7. So you have here 2, 4 heptadiene. You cannot choose 3, 5 because that is higher than 2, 4. So the correct name is 1, 2, 2, 4 heptadiene. Now, you may look also into consideration when there are two double bonds. So since there are two double bonds, I have to use the prefix di plus the ene, telling that it is an alkene. So hepta, meaning there are 7 carbon, and di, there are two double bond, ene, for alkene. So heptadiene. So we have here the sample problem. for the alkene. So we have basically we have the same steps. We have one, two, three. Analyze the problem, solve for the unknown, and evaluate the answer. And then we have here the given. And then of course, analyze the problem. You are given a branch chain alkene that contains one double bond and two alkyl groups. Follow the IUPAC rules to name the organic compound. And then the first one is solve for the unknown. For that, no, so the longest continuous carbon chain that includes the double bond contains 7 carbons. So you have to remember when you count the longest chain possible, make sure that the double bond is included. So you have here um, a heptene parent chain, no? So you have 1, 2, 3, 4, 5, 6, 7. So this is heptene, including in the chain is the double bond. Then for step 2, number the chain to give the lowest number to the double bond. So you have here 1, 2, 3, 4, 5, 6, 7. And then name each substituent. So the one that you did not include in the parent chain will become an alkyl group or substituent. So these are two methyl groups. So they are the same. CH3, these are two methyl. And then step 4, determine how many of each substituent is present and assign the correct prefix to represent the number, that number. Then include the position number to get the complete prefix. So you have counted here the 7, you have identified here the methyl, and then locate. No, the first one is found in the fourth carbon, so you put here 4. And the second methyl is found on the sixth carbon, so you have put here 6. So they must be separated by a comma, so that's why it is 4, comma 6 dimethyl. So since there are two methyl, you have to use the prefix di. And then the name of the substituents do not have to be alphabetized because there are only two. There is only one kind, no? So it is only methyl. So the name will be 4,6-dimethyl. Then location of the double bond found on the second carbon. So that is 2-heptene. So be mindful of the hyphen. So 4, 6 hyphen dimethyl hyphen 2 hyphen heptene. And first, you can also evaluate the answer. The longest carbon chain includes the double bond, check. The position of the double bond has the lowest possible number, check, because you have started on the left, not on the right. And correct prefixes and alkyl group names designate the branches. Okay. We have here the answer 4,6-dimethyl 2-heptene. So let us now look into alkynes. Again, unsaturated hydrocarbon that contains one or more triple bonds between carbon atoms in a chain are called alkynes. So their triple bond involve the sharing of 3 pairs of electrons. The simplest and most commonly used alkyne is ethine, which is widely known by its common name as ethylene. So straight chain alkynes and branch chain alkynes are named in the same way as alkenes. So the only difference is that alkyne end with YNE and alkene ends with ENE. So I do not have problem solving for alkynes because again, it is the same thing with alkene. So I just have here some common alkynes like ethine, propyne, 1-butene, and 2-butene. So you have here the molecular formula, the structural formula, and then the condensed structural formula. So you can see here that these ethine and propyne are both, well, of course, all of these are straight alkynes, showing the location of the triple bond. So in this case, you have here 1-butene. So it is located on the first carbon. That's why it is called as 1-butene. This one is located on the second carbon, whether you select to count it from left or count it from the right. So you have the same answer. So this is 2-butene. Okay. So This is not aromatic alkanes. Okay, so I'm sorry for the label. This is not aromatic alkanes, but these are alkynes. So properties of hydrocarbon. So we are done with alkanes, alkenes, alkynes, naming and formula. So let us look into some of the properties of hydrocarbon. So the size of the hydrocarbon molecules influences their properties, including their melting and boiling points. As a result, some of the hydrocarbons are gases at room temperature, while others are liquids or solids. So that's why, for example, methane, no, it is methane gas, the one inside our LPG tank. So they are in solid, in gas form, while others like butane, butane also is in gaseous form. Um, Hexane is in liquid form, and so on and so forth. So they are generally nonpolar, which means that their molecules do not have opposite charged particles. And because of that they are nonpolar, they do not dissolve in water, which is a polar compound. So in fact, hydrocarbon tend to repel water. So nagre-repel sila ng water. That is also why gasoline can float on top of the water, so they do not mix with water. So that's why they are used in floor wax and similar products. So when you apply wax, it repels water. So these are some of the properties of hydrocarbon. These are the melting point and boiling point of alkane. So what can you notice about their melting point and boiling point in relation to that of the number of carbons? So this one is 1 carbon, melting point is negative 183, boiling point is negative 162. Compared with 10 carbon, melting point is negative 95, boiling point is 69. And look into the C30, melting point is 65.9, boiling point is 451. So what can you say about their properties, melting point and boiling point? Would that affect the number of carbon when it comes with melting point and boiling point? Meanwhile, these are the properties of hydrocarbon in terms of alkene. So you have here ethene, propane, 1 butene, 1 pentene, 1 hexene, 1 heptene, 1 octene. So you have here the melting point, negative 169, going to the 8 carbon, becoming negative 102. Meanwhile, for the boiling point for ethene, there's only the boiling point is negative 104 degrees Celsius. Meanwhile, for octene, it is 121 degrees Celsius. So what can you say? Can the number of carbon affect the melting and boiling point? Can the number of double bond affect the melting and boiling point of alkene? So you have to analyze this. Another one is the property of hydrocarbon for alkynes. So you have here ethyne up to hexane, 3 hexane. So melting point from ethyne is negative 80.8. And for propine, it is negative 101.51. And then for pentine, it is negative 90. Meanwhile, for boiling point, it is negative 84 for ethyne, going to positive 55.5 for pentine. So what can you say about their melting point and boiling point? Now, let us look into the chemical reactions of alkanes, alkenes, and alkynes. So one of the reactions that can be shown by alkanes are their reactions to halogens. So halogens are those elements found in the under the halogen group, like chlorine, bromine, chlorine, iodine, and yeah. And then, for example, you have here methane with heat or light as catalyst. You have here chlorine. So it will lead into the formation of chloromethane and also the formation of HCl, which is an acid, but not an organic compound. On the other hand, when you use chloromethane as a reactant and mix it or combine it again with another atom of chlorine, it will produce dichloromethane and another HCl. Same process. So this time it is dichloromethane plus chlorine. It will lead into trichloromethane and acid. And when you do that again, it will lead this time to tetrachloromethane plus HCl. All right, so let us look into the chemical reactions of alkenes. So we have here three samples like halogenation, hydration, and hydrogenation. So for halogenation, it's the same thing as with alkene. Addition of um, halogen atoms or halogen elements. So in this first example, ethene is combined with bromine. So the result is a dibromoethane. So you'll notice that the degree of unsaturation or the double bond was reduced um, because of its reaction to bromine, leading to dibromoethane. So from alkene, it will become alkane because of halogenation. On the other hand, we have also hydration of ethene. So hydration meaning it is an addition of water. So ethene can lead to the formation of ethanol or known as ethyl alcohol. So ethyl alcohol is the component found in among wine as well as to our rubbing alcohol. So the one that we use to combat in the battle against COVID-19. So ethyl alcohol or ethanol. So you'll see there the functional group OH signifying that it is an alcohol. So ethanol. Another one is hydrogenation. So it is the addition or reaction with hydrogen or H2. So same or organic compound, ethene. So ethene plus hydrogen can lead to ethane, which is again an alkane. So you have here CH3CH3, which is an ethene. Okay, so you'll notice here that the alkene loses its um, double bond when it reacted with bromine or halogen, water, and hydrogen. So let us look into the reactions of alkynes. So you have here um, catalyst or it can also be reactant since it is part of the product. So you have here HCl, HBr, and bromine showing a slow reaction rate. So you have here C2H5. So you have C2 plus 1. So this is butane. 1 butane. 1, 2, 3, 4. Okay. So it reacted with HCl. Then the Cl of HCl was captured still in a double band formation. And then after that, but this time it is from triple band to double band. And then another reaction, this time it is again HCl. So same, no? However, it became an alkene. This time it is a dichlorobutane because there are two atoms of chlorine. Now, on the other hand, the same thing at the second equation, but it is instead of HCl, it is an HBr. So the same thing from alkyne to alkane, alkene, then from alkene to alkane. But again, um, it has halogen bromine. Now, you can also have here bromine itself, not not HBr, but bromine. So this time, instead of just two bromine, and just like the product for the second reaction, at the end of the reactions for this bromine, there will be four attached bromine in the formula. So yun. So these are the references for this discussion. So I hope that you have learned something from this video. And thank you so much for watching. See you again by next time. Thank you.